Today I'm going to show you a new and simple way to make an electronic downlight transformer. We just need two MOSFETs, two fast diodes, two capacitors, and a small ferrite ring transformer wrapped with 12 primary or 24 secondary turns. Here are two MOSFETs, very cheap, on heat sinks. Here are two fast diodes, fairly cheap. Here are two polypropylene capacitors, 100 nanofarads each. And here is our ferrite ring transformer wrapped with 12 primary or 24 secondary turns. To that I've attached a little LED downlight which rated for 12 volts. It doesn't come on until it reaches 10 volts. So let's turn on the power here and see what happens. It just starts to turn on at about 11 volts, half an amp. As we go a bit higher, 15 volts, it gets very bright. If we go to 20 volts, 1.8 amps, it gets extremely bright. So all brightness you could possibly want. So this method definitely works. Let's show you how I did it. Now here we have your basic half-bridge oscillator circuit that's used for halogen lights around the world. We have two transistors, T1 and T2, two capacitors, C1 and C2, and a primary coil which is coupled to a secondary, just like we saw in our circuit in a DC power supply. Often you put a wire choke here or a little 2 to 4 ohm resistor to limit the current. Now what happens is, this thing has two cycles. This is cycle 1. In cycle 1, the transistor is on here, T1, and T2 is off. The current goes around like that. In the top upper link, the bottom circuit goes like that. So C1 and C2 charge and discharge alternately as controlled by these T1 and T2 resistors. In cycle 2, T2 is on, T1 is off, and it does the reverse. So the current's going back and forth in AC fashion through the primary coil, and that makes the AC we just saw in the secondary. So clearly control of these T1 and T2 transistors during this process is critical. Now in the conventional downlight system, two transistors T1 and T2, it's a fairly complex circuit. Here's T1 and there's T2. You need a second transformer here to control feedback, second transformer to turn them on or off by feedback coils. It's a bit complicated, isn't it? And over here it won't start by itself. We have to have special components over here needed to start the thing. So I won't explain any more, but let's just see if we go to two MOSFETs here in 0 volt switching, we can do away with all that extra work. Let's see how that works now. Now in the standard circuit known for 0 volt switching, ZVS, we have a coil here which is tapped in the middle, the primary coil, and a capacitor in parallel with it to help the oscillation and control the frequency, and it can flip back and forth plus minus on both ends of that coil, and it starts plus in the middle, goes to the center, and then it can go plus minus on either side. And over here you have a MOSFET with its gate. Over here you have a MOSFET with its gate. And what they do is they have a fast diode go from the gate of the first MOSFET to just above the second one. And have another fast diode go from the gate of the second MOSFET to just above the first one. And that gives you alternate on-off switching of these two MOSFETs to create an AC frequency. And let's just review the physics very briefly how it works. Very simple and elegant. But we're going to do same gate MOSFET switching. So we have a MOSFET here with its gate, polarity plus minus, a 470 ohm resistor. If we put a fast diode here, there won't be any flow of that diode out of the gate if there's a plus minus voltage here. So this plus here will turn the MOSFET on. If on the other hand we have around the MOSFET we have a minus plus polarity, now current will flow through that fast diode from the gate into the minus, plus to minus, and this plus voltage will never reach the MOSFET to turn it on. The gate will be off. Next we're going to turn on the DC power from the supply over here, just to give you the most basic understanding of how this circuit functions. Now there are two MOSFETs in series, so we need 10 volts to turn on the current. See, at 5 volts nothing's happening. Each has a 5 volt activation energy. We get to about 10 volts, the current starts to turn on, but we haven't got any oscillation in the secondary coil yet. Nothing's oscillating. still DC. Now when we go to say 12 volts, when it really turns on, 0.8 amps, we have a 1.1 megahertz oscillation from that secondary. We can go higher quite easily, 1.1 amps, and we've still got a very stable 1.08 megahertz oscillation from this primary to the secondary coil. Here we have, just for the fun of it, two 10-volt LEDs lighting up in series. 10 volts, 15 volts, 20 volts, very bright, as bright as you could possibly want. This circuit will not only light up a 12-volt LED, which doesn't turn on until 10 volts, but it'll also light up low voltage LEDs like this red one. Here we are at 15 volts. Now it is worthwhile noting that this new method works for full bridge as well as half bridge transformer circuits. For the full bridge we need 4 MOSFETs, 2 fast diodes, 1 capacitor, and a small ferrite ring transformer. There are the 4 MOSFETs on heat sinks. Here are 2 fast diodes. And this is our ferrite ring transformer with a 12-volt LED attached, which will shine in a minute. Each of these new MOSFETs replaces a capacitor from the old half-bridge circuit. And then we have to add a new capacitor here, 100 nanofarad, in series between the ferrite ring transformer and MOSFETs T3 and T4 to make it work. Let's turn on the power now. We'll go straight to 30 volts. And at 0.65 amp, we get a nice glow from this LED light. This power supply isn't ready to go any higher than that. We'll turn the power down now to 20 and 0. So it's your personal preference whether you want to use a half bridge or a full bridge, and you can decide on your own. We can also add 2 12-volt LEDs in series to this full bridge circuit, and they turn on at about 15 volts. And then at 30 volts, 0.7 amps, they both shine quite nicely. To conclude this video, we're going to show a brief theoretical summary of how the new half-bridge and full-bridge circuits work with MOSFETs and fast diodes on the same gate. Now here's the half-bridge oscillator with 2 MOSFETs and 2 fast diodes. This is a schematic version of it. And in this first cycle, cycle 1, you see you have the 2 MOSFETs here with their fast diodes attached on the same gate. And current runs around according to that red loop, going that way through the wire coil. And it will attach to a primary. And MOSFET T1 is on here. And then we go into cycle 2 of the same half-bridge oscillator, and now T2 is on with its same gate fast diode, and the current goes the other way through a second loop. So we're not just charging and discharging one capacitor, we're charging and discharging 2. It's like filling a bucket of water here, then emptying it into another bucket of water, then emptying it to ground. It's like filling 2 different buckets of water and emptying them out in steps like that. So we get a lot of power from that device. No current goes directly through these MOSFETs. It all fills that capacitor, empties in that capacitor, then empties it into ground. So that's how the half-bridge oscillator works. Very simple and elegant. Finally, let us consider the full-bridge oscillator, which has 4 MOSFETs and 2 fast diodes. T1, T2, T3, and T4 are the MOSFETs, and the fast diodes are only on T1 and T2. It has 2 cycles, one in which the current goes left through the primary coil, another in which the current goes right through the primary coil. And that wouldn't create an oscillation, so we have to put a capacitor here in series with the primary coil as well. M is the primary coil, and that's the capacitor in series. It makes an LC oscillating circuit. Now what the fast diodes do here on the gates. There are only two of them. There's one on T1, but that result is linked through T4 through a wire. There's one on T2, and that's linked to T3 through a wire. So the gate voltages are linked. So as these currents switch back and forth through the LC circuit, these fast diodes with their gate wires automatically flip the MOSFETs back and forth. So we just have one bucket of water filling and unfilling here, unlike the two we had for the half-bridge circuit. You see two patterns of circulation here, red ink, and here you just see one in each cycle. So that's how these two circuits work, and you can choose whichever one you like. Our innovation here has been to use fast diodes on the same gate, like that, rather than 555 timers, anything very complicated, start transformers to make these two circuits work. Thank you very much.